so let's look at some examples then of molecules, observe what their steric numbers are, and then determine what the electron pair geometries for these three examples are before we move forward with the, let's say, slightly more specific molecular geometries. All right, so do your best. Look at the central atom, so boron, sulfur, and phosphorus. Determine how many electron groups there are around the central atom, and then figure out what its electron pair geometry is from that steric number. All right, welcome back from the fold. Let's start with our molecule here on the left. This is the molecule of BF3, Lewis structure, happily given. So what we're going to do is observe how many electron groups there are around each of the central atoms, the boron, the sulfur, and the phosphorus, starting with the boron. Well, in boron's case, or in this boron trifluoride case, we can see that there are 3 different bonds to the fluorines, and there are no lone pairs on the boron itself. Because there are no lone pairs on the boron, there are only 3 bonds around it. The steric number of this central boron is equal to 3. Since we have a steric number equal to 3, in order for these bonds to spread out as much as they can in 3D space, just to go back and look at our table that I'm going to clean up right now, the steric number of 3 corresponds to a trigonal planar geometry, which means that the molecule is going to have this shape in 3D. There are going to be 120-degree bond angle or bond angles between each of the fluorines as they surround this boron and spread out as much as they can. So our BF3 is going to have an electron pair geometry that is trigonal planar. All right, let's turn our attention to SO2. We can see that this central sulfur, yes, has expanded its octet. However, we are going to be looking for where the electron groups are. Where are the electron groups surrounding this central sulfur? Well, we can see that there is a lone pair up on top. There is a double bond down to the left and a double bond down to the right. Notice that I am not counting the double bond separately. This is one location. We are looking for the locations of where bonds are, not counting the numbers of electrons themselves. So we have one location down to the left, and we have another location down to the right, where another double bond is present. We have circled 1, 2, 3 locations for where electron densities can be, where we can observe that they are. This means that our steric number for our SO2 is also equal to 3. And a steric number equal to 3, if we go back upwards, corresponds to the exact same geometry that we just observed for the BF3. We are looking at a trigonal planar electron pair geometry. So our steric number equal to 3 means that we have a trigonal planar geometry. Right, and I did say that the steric numbers of 2, 3, and 4 correspond to molecules that are, at the very least, not expanding their octet, but it doesn't mean that expanded octets can't have these lower geometries as well. The higher level geometries must have an expanded octet. That is the rule. That is a prerequisite to have a steric number of 5 or 6, is you must have an expanded octet. If you have electrons kind of doubling up, like we have in this sulfur dioxide case, we can actually end up with a lower steric number, despite the fact that the central element has an expanded octet. So this is a really good example of kind of like, in form of an analogy, it's like how a square is always a rectangle, but rectangles aren't always squares. Here we have a steric number of 3 corresponding to an expanded central octet. All right, the last geometry we have to observe in terms of electron pair geometry is this phosphorus pentachloride, this PCl5. Now, just like before, we're going to observe where electrons are surrounding our central phosphorus. We can see that the chlorines are, some of them are like coming out of the plane of the slide. That's what this like big wedge means. Some, or one of these chlorines is going back behind the slide. So this is behind, and this is in front. It is our way of trying to illustrate the shape of these bonds, like how they're actually oriented, even though it's in 2D space, because it's a 2D drawing. All right, so let's count how many bonding pairs we have, or how many locations of bonds we have, how many locations of electrons around this phosphorus. You can see we have 1, 2, 3, 4, 5. There are 5 bonds and no lone pairs, meaning that our phosphorus pentachloride has a steric number equal to 5. So this is a great example of how we have a central element that has an expanded octet, and all of these electrons are actually spread out in 5 different unique locations. Because the electrons are spread out in 5 different unique locations, we are going to be working with, to go back to our table, steric number of 5, a trigonal bipyramidal geometry, this one right here. Right, a trigonal bipyramidal structure. So our chlorines up above and down below are right 180 degrees from each other. The chlorines that are presented here are kind of in this trigonal equator, even though they're not drawn exactly like that in 2D, right? Again, that's the limitation of trying to project a 3D image into 2 dimensions. There's always going to be a little bit of warping. All right, so if anyone has any questions thus far, if you were in my class, please do not hesitate to either leave a comment down below or shoot me an email directly. If you are not in my class, absolutely, please leave a comment below. I can do my best to try and explain or provide exterior links for like where we can rotate, and see these molecules in like 3D space.